Assalamu alaikum. I welcome all of you to the class. Today we will be studying reactions of carbenes, in which we will be again studying particular and very important reactions, Simmons Smith reactions, as we are studying the addition of carbenes across the double bond like that. This was a carbene, say it's a triplet or singlet, and this is some sort of a double bond. So we were, and cyclopropane was produced. As let me recall that the triplet state produces non-stereo specific products, and the singlet carbenes produced a stereo specific products. So now we will be studying another reactions which is called the Simmons Smith reactions. It's again nothing but addition of a carbene across the double bond. In fact, it's not a carbene. You will see these are the reagents. Suppose we take a cis-alkene, and these are Simmons Smith reagents, zinc with a copper powder. These are reagents CH2I2 and Et2O, diethyl ether, and it will produce a product. As this is a cis-alkene, so it will produce a cis cyclopropane ring. A cyclopropane ring in which the methyls will be cis to each other. So we can draw it like this. This is our cyclopropane. So this is one methyl, CH3 up, and this is the other methyl of CH3 up. So why we are studying this reaction? This reaction has immense importance, and you will come to know right now that why it's important. Suppose if we take a trans-alkene and place the same reagent into it, what will be the product? It will give us the trans product. Suppose this CH3 is up, now this CH3 is down, keeping the same reagents. Okay, reagents will be the same. Now, as I told you that here, when we see the reaction mechanism in a little bit depth of this reaction, we will come to know that this reaction doesn't involve a free carbene. It involves a carbene attached to some metal, so that is called as the carbenoid, and it is very good reaction. The yield of the reaction is very good. So let me write the mechanism of this, how the CH2 is delivered to the alkene. So let's take cis-alkene as an example. These are the methyl groups toward us outside the plane of the boat, and these are the hydrogens. This is a cis-alkene. These are there. Okay. Now let me write it. So all these become, this CH2I2 is the actual reagent. This CH2 is delivered as a carbene, and a cyclopropane ring is produced. The zinc metal, it helps in the delivery of the CH2 to the alkene, and this diethyl ether is used as a solvent. Okay, so it's, let me write it, CH2, the mechanism, zinc, iodine, another iodine, but at the same time, now this is not a free, as you see, this is not a free carbene like CH2. It is attached to the zinc and iodine, and it's something else. Actually, the zinc metal, first of all, the zinc metal is inserted into CH iodine. Actually, let me briefly say that how this thing is may be produced. So this is one iodine, this is another. This zinc inserts in between the CH2 and iodine bond, and it gives zinc. This is the iodine, and this is another iodine. It's just for you to understand. The zinc metal insert in this weak bond because it's metal and it is rich in electrons, so it provides electron to the sigma star of the Ci iodine bond and get itself inserted into it somehow. Okay. Now what will happen? Let me use another pen. So this, I am writing the transition state right now. Okay. So this bond will be breaking, and another bond will be making, will be starting develop, will be forming, and this will be finishing. Okay. So I'll write it as a hash lines. So another bond will be producing like this and like this. And ultimately this is a cis alkene, so we get a cis cyclopropane ring. If it were a trans, then we would got a trans alkene. So it's enough, because we should not repeat it for a trans, because it will consume an extra time of your. So it will be very important, it will be clear to you people that why the Simmons Smith reaction is very important. Let me write another molecule like this. It's a cyclopentane ring. Okay. Here it has OH and it has a double bond. Now, as the Simmons Smith reagents like zinc, copper, or these reaction conditions, iodine 2 in diethyl ether or a little bit heat. So when these reagents were placed into this alkene, they have wanted to study that how this alkene will behave, because now it has a OH group on its allylic position, or allylic position is the position which is adjacent to the double bond, the carbon which is adjacent to a double bond, and anything on this will be called as allylic. This is allylic carbon, and now this is allylic OH hydroxy group. So amazingly, and it's up. Okay, a product when produced, cyclopropane ring was produced, and the cyclopropane ring was up, just like this thing, because here the cyclopropane ring should be produced, and both of them were up, and almost this product was produced. This is our cyclopropane. Okay, this is cyclobutane ring, and the cyclopropane ring was formed above it. Okay, this is our cyclopentane, and so this thing is produced above it. It is not produced, no product like this was produced. This was the exclusive product, which this is now down. So this product was not produced, and only this product was produced. So how does this occur? As you know that the hydroxyl group, or the oxygen, it has some lone pair on it. Okay, and as you know that the metal can chelate with the OH with the lone pairs, because metals, majority of the cases, metals are in need of electrons, and they have some vacant orbitals in it. Now, right now, I should write the mechanism. How does it occur? I will try to write it, okay, that you will see. This is our wedge, okay. Now let me use another kind of a pen, another color. This is our zinc. Same thing with the previous iodine, we saw this. Here, as you see, this iodine is going out. This is the CH2 to be delivered, and this is the iodine. And as you see that the zinc, the OH made the zinc or the whole complex to come from its side, as the OH is above, okay, is above. So the propylene, due to the zinc and the OH chelation, the methylene will be delivered from the above side, okay. It's very simple, like you can see it. I don't have anything right now to show you, so let's see. This may be a little bit helpful. So suppose this is a cyclopentane. This is like this. It's cyclobutane, but assume this is or OH, okay, group. Now and this is or double bond, okay. Now the zinc will chelate with this thing, because the lone pair of oxygen will form a sort of a coordinate covalent bond with the zinc, because the zinc has empty orbitals, and now it is held like this in this position. So the whole complex is now above, because this thing is above up, and this whole complex is above, so it will deliver the CH2 from the above side. So this was a double bond previously. In the transition state, the sigma bond will remain, and the other bond will be start breaking, and ultimately we will get this product. So this is the beauty of the Simmons Smith reaction, that you can have a controlled stereochemistry, or it will give the good stereoselectivity or a regioselectivity in a sense that it will the propane will be formed on the above region, not on the below region, okay. So it's regioselective, and stereospecific. Also stereospecific mean that it is delivered from one side, okay. If it and it's also regioselective because it can see that from which region I should come. The OH attract the zinc, so it comes from the above side, and the below product is not produced. This is very important reaction. As this is Simmons Smith reaction is very important reaction, so the other scientists also developed it or modified it a little bit in order to improve it a little bit more. So I'll mention one reaction here. Suppose the same cycloalkene they have taken. This is cycloalkene. Now they have done a little bit modification into the original Simmons Smith reaction reagents. What they did, they placed diethyl zinc, and now here they place something else, which is the important part, CHI2, and the reaction was carried out in dichloromethane. But this R is very important, and you will see it, okay. Now what was the product of this reaction? As it is cis, it should have the same product like Simmons Smith reaction, but you have an advantage here. Again, it is a cyclopropane. Again, it will produce the same result like this cyclopropane, and these are the substituents. These are the cis methyls. but here they are cis, so I should write it like bold, okay. But another thing arises, this R can be this R also comes to the molecule. Now, so this means that here with this modification we can also produce or make substituted cyclopropane rings. Look at this. This R could be many substituent. R could be OR, OCH3, I mean OCH3. R could be hydrogen. R could be carboxylic acid or any other things. So you can do it is same reaction like the Simmons Smith reaction, but where you could just build or construct a cyclopropane ring, but here you can also substitution on the cyclopropane ring. So a substituted cyclopropane ring can be incorporated into alkene or added into an alkene. So it could also produce the same results like that. So if you take this same thing, right, okay, and let's say the isopropyl group, you take this big CH, R is equal to this thing, okay, this is or CH, and these are iodines. This is the R group, 1, 2, 3 propyl group, and the rest of the reagents are the same. ET2 zinc and dichloromethane. What will happen right now? Product will be the same because again you are involving metal, so the product will ring will be formed on the side where the OH is present. So the OH is above, the ring will be above. But now you have another thing which is very important. A cyclopropane and other 1, 2, 3. A substituted cyclopropane ring is made. So it is very important reaction.